Okay, revision for the paper 2. The paper suppose this 9702 and the paper 2, the revision for this. So the first chapter is the physical quantity, unit, and a vector. So physical quantity, a quantity which can be measured physically, and they are divided into group. One is the basic. They are 7 in number, length, measured in meter, time, second, mass in kilogram, temperature in Kelvin, amount of the substance in mole, electric current in ampere, and the luminance of light in candela. So these are 7 basic physical quantities. So the number 1 is the length, number 2 is the time, number 3 is the mass, temperature, amount of the substance, electric current, and the luminance of light, and the units are called the base units. And the rest of the physical quantities except angle theta are the derived physical quantity. And the derived physical quantity has 2 units. One is called the SI unit, in which it is measured, and the second is called the SI base unit, or simply the base unit, which gives the information which physical quantity, basic physical quantities are used in the derivation of this physical quantity. For example, voltage potential difference, V, is derived physical quantity. It has 2 units. One is the SI, other is the base. The SI unit is the volt, and the base unit we have to determine. So we will write formula. Voltage potential difference is work done per unit charge, F into D, work, and IT. Then put the unit, kilogram, meter, second power minus 2 for the force, meter for the distance, ampere for the current, time for the second. So when simplified, it becomes kilogram, meter square, ampere power minus 1, second power minus 3. This is one of the examples. And then if resistance is considered, resistance is equal to V over I, mean V is equal to IR. Resistance is measured in ohm, ohm is the SI unit. And for the base unit, this potential voltage has base unit, kilogram, meter square, ampere power minus 1, second power minus 3, divided by current ampere. So finally we can write kilogram, meter square, ampere power minus 2, and second power minus 3. And the next, the uses of the base unit. Base units are used in checking the homogeneity of the equation. For example, the equation is S is equal to UT 1 by 2 AT square. So this has 3 terms. If each term of the equation has same unit, then it's a homogeneous. So distance is measured in meter. The second term, meter per second, multiplied by time, second cancelled, it's also meter. And the third half has no unit, it's a number, acceleration, meter per second square, time, second square, cancelled, meter. So this is homogeneous equation. So base units are used to check the homogeneity of the equation. So this is one example. And the second use is to find the unit of any unknown physical quantity. For example, if it is written 6 pi eta RV, and it's given F is the force, 6 pi is the number, eta is the viscosity, R is radius, V is the speed. But suppose this eta is not clear. It's unknown physical quantity. So we have to calculate, we have to determine the unit of the eta. So we first make this subject of the equation. Eta is equal to F divided by 6 pi RV. The unit of the force, kilogram meter second power minus 2, due to F is equal to MA, 6 no unit, pi no unit, radius meter, and the speed meter per second. So 1 meter cancelled. Then finally it becomes kilogram. This meter comes up, it becomes meter power minus 1. When this second comes up, it becomes plus 1. So total second minus 2 plus 1. So we can write kilogram meter power minus 1, second power minus 1. This is another unit. But sometimes, for example, F is equal to K mv square over d. M is the mass, V is the speed, D is the distance, F is the force, and K is unknown. For example, this is the equation. And the question is, determine the unit of K. So we will make the subject K FD divided by mv square, kilogram meter second power minus 2, meter divided by kilogram meter second power minus 1 whole square, kilogram cancelled. So it becomes meter square second power minus 2 and divided by meter square second power minus 2. Look, no unit, it means it's a numerical value. It's a number. So if the units are there, it's a physical quantity. If no unit, answer is 1, then it is just a numerical value, not number 1, it's other value because it has no unit. And the next important is to determine the unknown power in any equation. For example, F is equal to m power x, speed power y, and the radius power z. And the question is determine x, y, and z. So we will write the base units of each. Kilogram, meter, second power minus 2. Mass in kg, its power x. Speed, meter per second, its power y. And the radius meter, its power z. So now to compare each unit one by one. Suppose first kilogram. The left side, the power of the kilogram 1, the right side it's x, so x1. Then compare meter, left side meter is 1, and the right side, the meter is y, and then z, so the powers are added, so y plus z is 1. Now, move to the next, second. Left side, the second is minus 2, and the right side, the second is minus y, minus cancelled, so y is equal to 2. So put this over here, 1 is equal to 2 plus z, so z is equal to 1 minus 2, means it's minus 1. So x1, y2, and the z is minus 1. So this is another use. Now, move to the next, the components of the vector. So coplanar vectors mean which are drawn at the single plane. So coplanar vectors are divided or resolved into two components. One is the x component and other is the y component. X component mean the portion of the vector which affects the object horizontally, and the y component part of the vector, portion of the vector which affects the object horizontally. Look, if this is a vector, any vector, force, So its x component, fx, is the vector itself, but its vertical component is 0. If the vector is like this, its x component is the negative x because it is directed towards the left, and the left side of the x is negative, and its y component is 0. If this is the vector, force vector, suppose velocity vector, its x component will be 0, but its y component will be the positive f. When the vector is directed like this, its x component is 0, but the y component is the vector itself. And now the vector is in this direction. It's making some angle with the horizontal line, theta. This is the vertical line. Now, when this vector is resolved into two components, this portion is the x component, and this portion is the y component. And do remember, the side up adjacent to the angle is always the x component, and side opposite to the angle, theta, is the y component. And both components are perpendicular to each other. And when both components fx and fy are added according to head-to-toe rule, then the resultant vector is determined. Now, fx formula, you have to remember, fx is equal to f cos theta, fy is equal to f sine theta, and then tan theta is equal to fy over fx, and fx square plus fy square and whole under root the magnitude of the vector f. So vector is a physical quantity which has magnitude, unit, and direction. But the scalar quantity has magnitude and unit only. It has no fixed direction. So magnitude, unit, direction for the vector. So in this syllabus, the first vector is the displacement. The second is the velocity. Then acceleration. Then all types of the forces, tension, centripetal force, weight. Then gravitational field strength, momentum, moment, electric field strength, magnetic field strength, which is also called magnetic flux density, and gravitational field strength. So this is the list of the vector physical quantities. And scalars are many: mass, density, pressure, power, electric current, resistance, voltage, all are the scalar physical quantities. Now, the application of the component is, if this is the slope, frictionless inclined plane, it's making some angle, suppose theta, with the horizontal. When the object is placed here, its weight is acting downward toward the center of the earth, but the reaction is perpendicular to the surface of the object. When weight is resolved into two components, for example, this line is extended, this line is extended, then do remember this angle theta and this angle theta. So 1, 2, 3, these angles are equal. Now, this line is representing the x component of the weight, and this line will represent the y component of the weight. So x component of the weight is balancing the reaction, and the wy component acting down the slope. If there is no force at the back of this block here, no force, then this wy is the unbalanced force, and unbalanced force will produce acceleration of the block, so it will slide down. So the unbalanced force is ma, and the wy is w sine theta. So ma is equal to mg sine theta, m cancelled. So slope acceleration is g sine theta if there is no friction. Now, if the object of any weight is hanging with the help of the two strings, and both strings are inclined at the same angle from the horizontal, then both are bearing the same tension. So this line is representing the x component of this tension. This line is minus Tx and the x component of this. And here, Ty for this and Ty component for this. Now, according to the rule, when the object is at rest, object in equilibrium, resultant of the forces is zero. Look, one force is weight acting downward, other is the right side tension, and then the left side tension. The resultant is zero. It's a closed triangle. And the sum of the x component must be zero. So Tx, this one, plus minus Tx, this component, this weight is acting downward, so its component x is zero. So plus zero, the answer will be zero. Similarly, the sum of the y components will be zero. So Ty plus wy is minus w, vertically downward, y-axis negative. So minus w, 0. It means 2 times Ty is equal to w, balanced. So from this, we can write 2t sine theta is equal to w. And this equation can be used for the calculation of the tension, w divided by 2 sine theta. This is a calculation. But when you have to draw this, draw the line for the weight, for this right side tension, this angle is 90 minus 30, 90 minus theta. So here 90 minus theta. For example, this is 30 degree. This will be 60. So here we will draw the 60 degree angle. So draw the line at 90 minus theta. Similarly for this one, this horizontal angle is theta. The vertical will be 90 minus theta. So again here 90 minus theta. This one. So this line will represent the tension at the right side. This will represent the tension at the left side. So by the scale drawing, we can determine tension in each, or calculate this from this one. Now, the next is the measurement for the next chapter, which is called the measurement technique, chapter number 2. For the measurement, first portion is a reading, actual reading, and the second is the absolute uncertainty. The reading and the uncertainty has same unit. But when uncertainty over reading is calculated, this is called fractional uncertainty. And when uncertainty over reading multiplied by 100 is calculated. This is called percentage uncertainty. Fractional uncertainty, percentage uncertainty has no unit. Now there are the errors. Number one error is called the systematic error, which is due to the faulty instrument, due to wrong assumption, due to limitation of the observer. Faulty instrument means the zero error. Wrong assumption means you are using G value 10 instead of 9.81, and the limitation of the observer reaction time. So this is systematic error. Now the property is it does not fluctuate both sides of the true value. If first time it's higher than the true value, next time will be higher. It cannot be reduced by taking the average of the several reading, but if it's due to only faulty instrument, then by replacing the instrument, we can eliminate it. And if the systematic error is minimum in the reading will be considered the accurate reading. So minimum, the systematic error, maximum, the accuracy. And the second is the random error. This random error is due to surrounding unavoided physical conditions, due to parallax situation. It fluctuates both sides of the true value. It can be reduced by taking the average of the several reading, but it cannot be eliminated completely, entirely. And the reading with the minimum random error is considered the most precise reading. Now the question is, what is the precision and accuracy? If the value is close to the true value, then the degree of deviation from the true value is called the accuracy. Mean, if the value is very close to the true value, then it is accurate. Minimum the degree of deviation from the true value, maximum the accuracy. But for the precision, we have to compare the reading with each other. The degree of deviation among the reading. If the readings are very close to each other, then they are precise. For example, if the true value of the G is 9.81 and the two values are coming, suppose 7.81, 7.80. So these values are not accurate, but close to each other. So they are precise. And the next is significant figure. So look, the left side zeros are not significant. So this is too significant figure. And the zero between the two numbers mean the sandwich zeros. They are significant. So 1, 2, 3, 4. This is 4 significant figure. And the next right side zeros are not significant. This is not significant. This is not significant. So this is too significant. But sometimes they are considered significant. So we can say this is too significant or this is 4 significant. So we can write them according to the requirement. So this is too significant. This is also the 4 significant. But if there is a decimal in the reading, then 100% these zeros are the significant figure. This is not too significant figure. Now this is 100% for significant figure. And the next, if we are calculating any quantity from any formula and we are using same number of the significant figures, for example, the mass is 2 significant figure, the acceleration is 2 significant figure, and F is equal to ma, when force is calculated, the answer will be quoted in 2 significant figure or 1 better significant 3 significant figure will be acceptable. But if the mass is in 1 significant figure acceleration is in two significant figure. If different significant figures are used, then the force must be written in one significant, mean minimum number of used significant figure. You have to write the answer. And the next, different estimations. For example, mass of the human head, mass of the protector, atmospheric pressure, density of the water, density of the mercury, density of the air, mass of the athlete, maximum speed of the athlete, maximum kinetic energy of the athlete, maximum resistance of the filament lamp. Like this, you have to learn some estimation for this paper. And the next is the calculation of the uncertainties, that is called the compound error, or the errors in the calculation. For example, this Q is equal to A plus B. Then the Q is calculated by the addition of A plus B, but when the error is required, delta Q, both errors are added. So readings are treated according to the operation. Mean for the addition, we will add them. For subtraction, we will subtract them. But for the calculation of the uncertainty, for both addition and subtraction, we have to add errors. And if the question is Q is equal to A minus B, then for the error of the Q, we will add both errors, delta A and the delta B, both are added. But in multiplication, in division, and in the index, mean the power, for example, F is equal to mv square over r, reading is determined from the formula, F is equal to mv square over r, but the error is calculated either by the fractional uncertainty, addition of the fractional uncertainty, or by the percentage uncertainty. Look, the fractional uncertainty of the force is this. Fractional uncertainty of the mass, this is V square, mean 2 times delta V over V. The power becomes the multiple of the fractional uncertainty, and plus delta R over R. Whether it's multiplied, divided, you have to add the fractional uncertainty. And finally, for the error, delta F is equal to delta M over M plus 2 times delta V over V plus delta R over R times F, and this is the uncertainty. Then you have to write the justified answer significant like this. Okay, so then the measurement from the CRO, if the time period is required, then the formula is time-based setting multiplied by number of the horizontal boxes of the one wave on the grid. Time-based setting multiplied by number of the horizontal boxes covered by one wave horizontally, that's a period. Then frequency is equal to 1 over time period. And if the voltage is determined, then the voltage is vertical gain setting multiplied by number of the vertical boxes from the mean position. For the positive voltage, we will count the upper number of the boxes, and for the negative, lower number of the boxes. For example, this is the line and this one. So 1, 2, like this. So 1, 2, 3, 4 boxes vertically for the positive voltage, and similarly 1, 2, 3, 4 vertically. Usually both peaks are of the same amplitude, but if they are of different, then definitely they will ask for the positive and negative voltage. So the vertical gain setting multiply with the number of the vertical boxes from the equilibrium line, from the mean line, this will give you the voltage. So this is chapter 1 and this chapter 2. Okay, now move to the next chapter, which is kinematics number 3. So you have to remember the definition of the displacement. It is the distance between two fixed points in a specified direction. then the velocity, the rate of change of displacement, and the speed, rate of change of distance, and acceleration, rate of change of velocity is acceleration. And do remember, distance is equal to speed times t, or distance s speed times t. This is only valid when speed is constant. If the speed is changing, then this is not the valid equation. Then we will write s is equal to u plus v over 2 into t. And then derivation of the first equation of motion, acceleration is the change in velocity divided by time. So a is equal to v minus u divided by t, which can be written as v is equal to u plus at. And then by using this and this equation, you can determine the second and the third equation. For example, for the second, s is equal to u plus v divided by 2 times t. Now, substitute this v from this equation first. S is equal to u plus, instead of this v, you can write u plus at divided by 2 into t. And then equation will be s is equal to 2u plus at divided by 2 into t. Now multiply this t with both. So s is equal to 2ut at square, and then divide this 2 individually. This 2 cancelled. So your second equation is there. S is equal to ut plus 1 by 2 at square. And this equation, v is equal to u plus at, first one, and the second, these are valid only when the acceleration is constant. When acceleration is constant. And similarly, you can determine v is equal to u square, v square is equal to u square plus 2as. And for this equation, this one, this acceleration is also constant. If the graph is required between v square and the distance s, initial speed 0, definitely it will be a straight line, and the gradient will be double of the acceleration. But if the question is, sketch the graph, distance here, and v here just, then the graph will be like this. Because for this second graph, it can be written as v square 0 plus 2as, or v is equal to 2a over vs plus 0. This distance x, s is at the x-axis, v at the y-axis. This is the gradient. Look, this 2a is constant, but the velocity, the speed increases. When speed increases, denominator increases, the whole fraction decreases, mean the gradient decreases. So this is decreasing gradient curve. Now the next, in projectile motion, the horizontal force is 0 in the absence of the air, and the vertical force acting is the weight. So the horizontal acceleration is 0, mean the horizontal velocity is taken constant, change in velocity x0, so mean vx is constant. And due to this weight, w is equal to mg, acceleration is plus minus g. So vy is changing both in magnitude as well as in direction. And number 3, in the absence of the air, time of the free fall from the certain height exactly equal to the time of the projectile from the same height. And this horizontal distance is covered due to horizontal velocity, and this vertical height gained or lost is due to the vertical velocity. So Vx is responsible for the horizontal distance. Vy is responsible for the vertical distance. And for the time, one side, top to bottom or bottom to top, t is equal to v sine theta over g. For total time of the flight, it becomes 2v sine theta over g. And for the vertical height, you can apply formula s is equal to ut plus half t square. Our height is equal to v square sine square theta over 2g. And for the horizontal distance, mean the range, you can apply s is equal to ut plus half t square. So acceleration is 0. Horizontal acceleration is 0. Horizontal acceleration is 0. So s is equal to just ut, and range is equal to v square over g sine 2 theta. But for the maximum range, formula is v square over g because sine 2 theta used 1. So theta must be 45 degree. Now this is the path of the projectile motion. Here is the velocity initial with which it's thrown. It's making some angle theta with the horizontal. This is Vx, which is constant. This is Vy, vertical component. But at this point, the Vx is same in magnitude, same in direction, but the Vy decreases. And at this point, only Vx, no Vy. At this point, the Vx is same, but the Vy is now increasing in the opposite direction. So horizontal acceleration 0 in the absence of the air. Now, if the air is there, then definitely the air will oppose the horizontal component and the vertical component both. Then this will be the path of the projectile in the presence of the air. Mean this is the trajectory in the absence of the air, and this is the trajectory in the presence of the air. Okay, now equations are V is equal to U plus AT, first equation. Second equation is S is equal to UT plus 1 by 2 AT square. The third equation is V square is equal to U square plus 2 AS. Acceleration constant, then valid, but when the object is falling down in the equation, we will put plus G. When the object is thrown up, we will use minus G. So we have to consider only the change of the velocity downward. Downward, the velocity increases, so positive acceleration. Upward, the velocity decreases, so negative acceleration. But if the acceleration is discussed other than equation, then direction will be given. For example, if in the paper the direction is given, this downward is taken as positive. Acceleration has magnitude and direction. So magnitude depends on the velocity. Velocity downward increases and multiply. Direction downward given is positive. So downward, this acceleration positive. But if the object is thrown up and the positive direction is downward, then for the upward journey, the magnitude of the velocity decreases. And this direction upward with respect to given direction is also negative. So this is positive. But do remember, this concept is not used in the equation because equations deal only with the magnitude, not with the direction. So if the direction is mentioned in the paper, downward take downward positives, and up and down both will be positive. If upward direction is given in the paper positive, then acceleration, which has magnitude and direction. So for the downward motion, magnitude of the velocity increases, but this direction is opposite to the given direction, so negative, so minus g. When it's thrown up, velocity, magnitude decreases, and the direction is similar to selected direction, so it's positive, again minus g. But do remember, this concept is not used in the equation. Now, the graphs for the speed against time graph, the gradient is acceleration. And the area under the graph is equal to distance. For the velocity time graph, it will be displacement. And next, if the graph is plotted between acceleration against time, then the gradient is nothing but area is equal to final speed if initial speed is 0, and area is equal to just change in speed if initial speed not 0. Then if the distance against time graph is plotted, the gradient is speed. If displacement time, then the gradient will be velocity and area nothing. Now, if suppose this is the graph, this is velocity time or speed time graph, its acceleration graph will be, look here, the positive acceleration, it's constant. For this portion, there is no acceleration. And for this, acceleration is constant but negative. This is a graph. And for the distance, gradient of this graph is the speed. Look, the speed is increasing initially. So we will start from the 0 gradient, because the initial speed is 0. It increases. Then here the speed is constant, so gradient constant, straight line with scale. And then here the velocity decreases, finally becomes 0. So gradient decreases, and finally the horizontal line. So these are the graphs. And the next important is, if the object is falling down, if the object is dropped in the air, initial speed is 0, initial acceleration is taken plus g, weight acts downward, thrust upward, and air resistance, drag force upward. Initially, weight, suppose 20 Newton. Throughout the fall, it remains 20 Newton. Thrust, which is the force due to pressure difference, it acts upward from high pressure to low pressure. Suppose initially the thrust, up thrust is 2 Newton. Throughout the fall, it remains 2 Newton. But the air resistance, it depends on the magnitude of the speed. Initially speed 0, so air resistance also 0, but gradually increases. So when the graph is plotted, time at the x-axis, and these forces at the y-axis, the weight is the maximum force which remains constant. Thrust is the minimum force which remains constant. And the air resistance starts from 0, it increases, and then becomes constant. This is air resistance, this one. And the difference of the forces mean the resultant force. The resultant force here mean the unbalanced force will be weight downward minus the sum of upthrust plus air resistance. And this resultant force gradually decreases. When the resultant force becomes 0, when the sum of the thrust and the air resistance becomes equal to weight, object falls further with a constant velocity, with a 0 acceleration. So the resultant force decreases. Initially, the resultant force is maximum. It gradually decreases, and finally it becomes 0. So this is weight, this is thrust, this is air resistance, and this is resultant force. And the acceleration depends on the resultant force. So the shape of the graph for the acceleration will be similar to its force graph, this one. And then if the object is dropped in the absence of air for the several bounces, then the velocity time, not the speed time, the velocity time graph will be like this. When it is dropped from the height, initial speed 0, it increases. Then it hits the ground, its magnitude becomes 0. Then it rebounds after losing some energy, losing some speed. So this height and this one, different. And then it rises up. So this is the fall, and this is the rise. So this area is the x, mean the fallen height, and this area is different because it rises to the less height after losing some energy. But again, it falls back from the same height. It hits the ground second time. But do remember, this area we have to keep same, equal to y, because the height gained and height lost same. And then it goes like this. So this is fall number 2. This is rise number 2, and so on. But this will be the different because after the bounce, it will rise to the less height. But do remember, all these lines are parallel to each other because gradient is constant, acceleration is constant, and all gradients are positive, whether it's rising, falling. We are not using the equation here. We are considering the direction as well. So we have to keep either acceleration up, down, both positive or both negative. And then if the graph is plotted for the acceleration, this acceleration initially constant g, when it hits the ground, it retards to rest and it accelerates in the opposite direction. For that short period of time, the acceleration is negative, mean during the contact with the ground, it has negative acceleration. But after leaving the ground, it has again g. Then second time it hits the ground. Now the change of the velocity is smaller than the previous. So small retardation. And then it leaves the ground. It moves up. So this is acceleration. Now, This gap, this one, is showing the contact period with the ground. This is negative acceleration. This is a negative. So here the first bounce contact, second bounce contact, velocity change is different. Look, this value and this value difference is greater than these two value difference. That's why this negative retarded, this negative acceleration is due to this change of velocity, and this negative acceleration due to this change of the velocity, this acceleration time graph. Okay, now next important. If this is the object, is falling down, its weight is 20 Newton. At some instant, this upthrust is 2, and the air resistance is 5. Now the question is, what is the resultant force? The resultant force, the unbalanced force will be 20 minus 2 plus 5 is 13 Newton. When the object is thrown up, suppose at some stage, weight same, the thrust same, 2 Newton in the same condition, and the air resistance now opposing the motion, because here the object is falling down and here it is thrown up. So air resistance will be acting down. Suppose it's 5 for the same speed. Now the resultant force will be 20 plus 5 minus 2. So this is 23 Newton. It means the accelerating force is 13 and the retarding force is 23. So when the object is thrown, when the object is dropped in air, downward resultant force is smaller than the upward retarding force. So the acceleration, positive acceleration, and this retardation, negative acceleration, when compared, they are not equal. Retarding force is always greater than the accelerating force in the presence of the air. So when retarding forces are different, accelerating forces are different, then acceleration is the change in the velocity divided by time. If we take the same change of the velocity, for example, object is dropped from this. Here, the initial speed is 0, and here it reaches with 12 meters per second. Again, it's thrown up with 12 meters per second. It reaches the height, and its final speed becomes 0. So look, the change is 12, changes 12. But here downward, action is small, and here the retardation is large. Okay, now small acceleration, large retardation, change of velocity same. So acceleration is inversely proportional to t. When acceleration is small, it takes longer time to gain this 12 meters per second. But here the retardation is large, so it takes longer time to reach the 0 velocity. So 0 to 12 downward time will be greater, but upward 12 to 0 time will be smaller due to different resultant forces, different acceleration, different retardation. Okay, now move to the next, which is dynamics, number 4. In dynamics, the most important is the momentum. Momentum is the product of mass and velocity. So when the momentum is 0, or the momentum P is constant, it means we are obeying the Newton's first law. When the momentum is 0, the object at rest. When the momentum is mv, it's constant. It means we are following the uniform motion. So the forces are balanced. Forces are balanced when the momentum is zero or the momentum is constant. But when we will apply unbalanced force, definitely it will produce acceleration due to change of velocity. So the momentum changes. So the delta P is equal to m delta V. The base unit of the momentum, kilogram meter per second. It means for the zero momentum or for constant momentum, balanced forces are required. And for the change of momentum, unbalanced force is required. So this is the Newton's first law, and this is the Newton's second law. So the Newton's first law is, in the absence of any unbalanced force, object will continue its state of rest or of uniform velocity. And the ability of the body to maintain its state, to resist against the change of state, is called inertia. That's why sometimes the Newton's first law is also called the law of inertia. But in second law, the forces are unbalanced. So look, the change of the momentum is m times delta V. Unbalanced force required. So unbalanced force, F is equal to ma, which is actually equal to driving force minus resistive force. Mean resultant force is equal to ma, so F is the resultant force. It can be written as F is equal to m times change in velocity divided by t. So F is equal to m delta V over t, mean change of momentum divided by time. So this is the important equation. If we state it like this, rate of change of momentum is equal to force. Rate of change of momentum is equal to force. That is the force definition. If we state it like this, rate of change of momentum is an unbalanced force. That is the definition of the Newton's second law. If the graph is plotted between momentum and time, then its gradient is equal to unbalanced force. And the change of momentum is also equal to unbalanced force times t. So force Newton times second, this is the SI unit of the momentum. And if the graph is plotted between force and time, then the area is equal to change of momentum. And if the time is very, very small, equal to your reaction time, then this change of the momentum is called impulse, and the force is called impulsive force. If the unbalanced force is exerted for the very short interval of time, then the change of momentum is impulse, and this is impulsive force. Momentum is a vector. It has direction similar to the velocity. Now, the Newton's third law is every action has a reaction equal in magnitude, opposite in direction, and kind of the forces is same. Kind mean balanced, unbalanced, not the types of forces. There are many types, but there are only two kinds. One is the balanced, other is the unbalanced. So FA is equal to minus FB. If action force is balanced, the reaction force is also balanced. Equal in magnitude, opposite in direction, acting at two different objects. If action is at A, then the reaction will be at the B, but the time interval will be same time interval. But if the forces of action and reaction are unbalanced in third law, then we can write according to the Newton's second law, resultant force, unbalanced forces, change of momentum divided by time. So this is another form of third law. Both timings are same. So we can write change of momentum of A is equal to change of momentum of B. And the change of momentum is Ft. So FTA minus sine FB TB. So this is another form. Now this can be written as final momentum minus initial momentum of A is equal to final momentum minus initial momentum of B. Mean if graph is plotted between momentum and time, Newton second and second Hare units, if suppose this is the momentum of the object A, suppose it's 7. And this is the momentum of the object B, suppose it's -5. Mean both are in the opposite direction. This object A is going in this direction with 7 Newton per second, and this object B is moving in this direction with -5 Newton second. And they are about to collide. Suppose this is the point of the collision. And after collision, if the momentum of the object A becomes -3, so this is -3. So this is the initial of A, and this is the final momentum of A. So now what is the change of momentum of A? The change of momentum of A, final minus initial, mean -3 minus 7 is -10. Now, according to Newton's third law, the change of momentum of A must be equal but opposite in direction. So, after the collision, then the momentum of B must be positive and 5 in magnitude. So this is the initial of B. This is the final of B. What's the change? 5 minus -5, it's 10 plus. Look, both are equal in magnitude, one positive, other negative. So this is the graph for the Newton's third law. But we have done that if the graph is plotted between P and T, momentum and time, that the gradient is force. So look at the gradient. This is negative gradient. And this is the positive gradient. So if this gradient is the action force, then this gradient will be the reaction force, but opposite. So the gradient of these two lines from this A point to this B point, and then C to D, these are showing the action and reaction forces. Now move to the next. This equation can be written as MAVA minus MAUA is equal to minus MBVB and plus MBUB, which can be written as MAUA plus MBUB is equal to MAVA plus MBVB. So this is called law of conservation of momentum. Total momentum before collision is equal to total momentum after collision, but only two objects are involved in the collision, which is called the isolated or closed system. So the definition will be in an isolated system or in any closed system, the sum of momentum before collision is equal to sum of the momentum after collision, or total momentum before collision is equal to total momentum after collision. So it is derived from the Newton's third law. Now, if the objects are interacting with each other, there are two types of the collision. One is perfectly elastic, or simply call it elastic. For elastic, momentum is conserved and the total energy is also conserved. Total energy is also conserved. Kinetic energy is also conserved. So for the elastic collision, momentum conserved, total energy conserved, total kinetic energy conserved. Mean the kinetic energy total before collision is equal to total kinetic energy after collision. But for inelastic collision, momentum is conserved, total energy is conserved, but the kinetic energy total before collision is greater than kinetic energy after collision. Mean kinetic energy is not conserved. And one more thing, the intensity of the collision can be determined by the relative velocity of approach towards collision. For example, this object is moving with velocity 7 meters per second. This is at rest. And in the second case, this object moving with 7 meters per second velocity, this object moving in this direction with 2 meters per second. And in the third case, this object is moving 7 meters per second, and this is going in the opposite direction with 2 meters per second. Now, number one, number two, number three, definitely this head-on collision will be the strongest one. And this is the weak collision. And this is the medium collision. Reason. Look at this. Relative velocity of approach is u1 minus u2. For this, 7 minus 0, the answer is 7. For this, u1 minus u2. This is 7. This is 2. So it's 5. And for this, u1 minus u2, 7. These are the velocities. So this is the negative velocity. So minus 2, this is 9. So greater the relative velocity of approach towards collision, stronger the collision. And there is also the relative velocity of approach. If the collision is perfectly elastic, then the velocity of separation is equal but opposite in direction to the velocity of approach. For the elastic collision, mean V1 minus V2 is equal to minus U1 minus U2. But for the inelastic collision, both are not equal. Now, momentum is a vector. If the momentum is linear, mean before and after the line of the motion remains same, straight line, forward, backward, line straight. This is the linear momentum. For the linear momentum, collision must be head-on. But sometimes when two objects collide, they move in different direction. That's called the angular momentum. Momentum is a vector, so we will resolve them into components. X component conservation, Y component conservation. For the X component, we will write M1 U1 cos theta 1, M2 U2 cos theta 2 is equal to M1 V1 cos theta 3 plus M2 V2 cos theta 4 for the X components. And for the Y components, similarly, we will write M1 U1 sine theta 1, M2 U2 sine theta 2 is equal to M1 V1 sine theta 3 plus M2 V2 sine theta 4. So we have to write their X component formula and the Y component formula. For example, one object is moving in this direction. Other object is moving in this direction. And after collision, one of the object is going in this direction and the other object is going in this direction. So this is 1, 2, 3, and 4. So we will write the angles. This angle is θ1. This angle is θ2. This angle is θ3. This angle θ4. So we have to follow this rule. Okay, next is the force, density, and the pressure. The first is the moment, the torque, and the moment, not momentum. Moment, which is torque, which is turning effect, is defined as it's a product of force and its perpendicular distance from the pivot. So the torque is F times D, but D must be perpendicular and the unit Newton meter. And if distance is not perpendicular, then the torque will be FD sine theta, the angle between force and the distance. For the coupled torque, look, this is the pivot. This distance suppose D1, this distance D2, one force in this direction, other in this direction. Both forces are equal, opposite, and rotating the object in the same direction. So they are making the couple. Then the couple torque is equal to FD1 plus FD2 and F common D1 plus D2. And the definition will be, it is the product of one of the force from the couple, one of the force, and the total perpendicular distance between two forces. If both forces are not at 90-degree angle, then the coupled torque will be F D1 plus D2 sine theta. Now, condition of the equilibrium is the resultant force is 0 and the resultant torque 0. If the object is at rest, then the resultant of the all forces acting on the object must be 0. And number 2, the resultant torque of the all forces, mean the resultant torque is 0. Mean the resultant of all torque produced by the forces must be 0 about the common pivot. So the principle of moment is, in the state of the equilibrium, sum of clockwise moments must be equal to sum of anti-clockwise moments. Okay, for example, this is vertical wall, this is the rod. It is held stationary with the help of the string. Now, one force acting downward is the weight of the rod, and other is the tension. Now, forces are not parallel. System is in equilibrium. If the forces are not parallel, do remember, then all forces acting in the system must meet at a point. Now, the third force, which is acting here, the reaction of the wall, must meet these two forces here. So this is the direction of that force. Because the resultant of the force 0, resultant torque 0. So three forces will meet at a point, single point, to produce the resultant torque 0. But in this case, one force acting here, other force acting here, if the object is in equilibrium. Forces are different. Resultant torque 0, distance will be different. So the relation between force and distance is this, both are inversely proportional. Larger the force, smaller the distance from the pivot. If D2 distance is smaller than D1, definitely this F2 is greater than this. In this case, third force acting is upward, which is the reaction. We will ignore the turning effect of the R because it is exerted at the pivot. It has no turning effect. But do remember, these forces are not meeting here because they are parallel. So in this situation, we will write sum of upward forces is equal to sum of downward forces. But here, when the forces are non-parallel, they must meet at a single point to produce the resultant torque. Now, density, next one, simple, scalar, mass per unit volume. And the mass is equal to density multiplied by volume. Density is measured in kilogram per meter cube. If it is given in kg per centimeter cube, multiply it by 1000, it is converted into kg per meter cube. And pressure then, pressure is equal to force divided by area. It is measured Newton per meter square, which is called the Pascal. And the pressure is exerted sometimes due to the weight. So W divided by area. Weight is equal to mg divided by area. And m is the density multiplied by volume multiplied by g divided by area. So the pressure is equal to density, volume, area into height into g divided by a. So cancelled. So the pressure is equal to rho gh. Mean the pressure is directly proportional to density, and the pressure directly proportional to h, and the h is the depth here, not the height. So do remember, if this is the depth, this is the pressure, it's like this. If the h is taken here, then this is a graph. And the gradient of the both will be density times g, density times g. When we have to calculate the density, the formula is mass per unit volume, and the volume of the object of the sphere 4 by 3 pi r cube. Okay, next. Work, energy, and power. What is the concept of the work? When force is applied on the object and the distance is covered by the object in the direction of the force, then the work is done. What is the definition of the work? It is the product of force and distance covered by the object in the direction of force. Work is scalar. First formula, Fd, when force and distance both are in the same direction. Work is equal to Fd cos theta when force and distance are not parallel. If the work is done by the gases, then pressure multiplied by change of the volume. Work is done to change one form of the energy into the other form. That's why the work is equal to change of energy. Now, what is energy? Energy is the ability of the object to perform some work. Work is a scalar, energy is scalar, both are measured in joule. There are many types of energy. For example, the first one is the kinetic energy. So the change of the kinetic energy is equal to work, and the work is Fd. When the object is at rest, we have to apply unbalanced force. So unbalanced force will be equal to ma. And the distance covered by the object from one point to the other point, initial speed is 0, final speed is there, it has some acceleration. So we can write v square is equal to u square plus 2as. When u 0, then v square divided by 2a is the distance. So we can write ma times v square over 2a, a cancelled. So it becomes half mv square. Okay, so it's a formula. Sometimes it is linked with the momentum. Momentum is mass into velocity. So the velocity is equal to P divided by M. So kinetic energy 1 by 2 mv square mean 1 by 2 m. Instead of v, we will write p by m. So p square over m square due to square. 1m cancelled. So kinetic energy, other formula will be p square over 2m. This is kinetic energy. Similarly, potential energy. Definition of the kinetic energy is energy possessed by the object due to its speed to do some work. And the potential energy is the energy which is stored in a body to do some work. It has many types. Number one is the gravitational potential energy. This gravitational potential energy is energy stored in a body due to height of the object, due to position of the object to do some work. It is equal to also work. And the work is Fd. To lift the object, the minimum force required is the weight. And the distance covered is called the height. So formula will be mgh. Next, potential energy is the elastic potential energy. Energy stored in a body due to its deformation to do some work is called elastic potential energy. So elastic potential energy is also work. And the work is Fd. In deformation, initial force is 0, which increases gradually and finally becomes maximum. That's why we have to write here the average force times d. And the average force is equal to initial 0, final force divided by 2, multiplied by distance covered by the molecules, mean the extension. That's why it is 1 by 2 fx. And the next is the electric potential energy, energy stored by the object due to separation of the charges to do some work. So electric potential energy is also work, and the work is charge multiplied by potential difference. So these are the few energies. Important, yes. Then nuclear energy, energy stored, energy extracted from the nucleus of the object during fission or fusion is called nuclear energy. There are many types of energy. And the next is the power. The power is defined as work done per unit time. This is the definition, work done per unit time. So the power is equal to work divided by time, energy divided by time. So power is measured in joules per second, mean watt. Now power, work mean force into distance divided by time. So distance divided by time is the speed. So force times speed. Power is equal to force times speed. This is another formula, but if the object is falling down So the force which is bringing it down is the weight. So in this case, the power will be equal to mgv, force into speed. But if the object is moving in this direction, inclined direction, then the component of the weight is bringing it down, not the whole weight, then the power will be mgv sine theta. Now the graph, suppose power and the speed is directly proportional, then the gradient will be equal to the force, and then efficiency, simple, output energy over input energy. For the percentage, multiply by 100, output power over input power, and the equation is input energy is equal to lost energy plus useful output energy. This is the equation. Okay, look at the few graphs. If gravitational potential energy and the distance covered by the falling object is plotted, so it's a graph, and the gradient will be the mass into g acceleration due to gravity. If the x-axis is height, that at the zero height, definitely the potential is zero, so the gradient is constant, mg, m constant, g constant. Now, kinetic energy, distance covered by the object, kinetic energy in the absence of the air is a straight line passing through the region in the absence of the air. But if the air is considered, the falling object may achieve terminal velocity, then this is the graph for the kinetic energy. And the kinetic energy gained the maximum is not equal to the maximum potential energy at the height. This is the potential energy. So the potential energy value will be greater than the kinetic energy achieved on hitting the ground. Reason, because the sum of the energy is lost in overcoming the air resistance. So this is a graph in the air. This is for the kinetic energy, and this is for the potential energy. Now move to next. Next chapter is the deformation in solid. So first of all, deformation in solids, the change in length, change in dimension. It is represented by delta L x E, any symbol. And it depends on original length, directly proportional to original length, directly proportional to change of temperature, inversely proportional to cross-sectional area, inversely proportional to the material constant, and directly proportional to the load. Now the solid has two properties, elasticity, plasticity. If the load is applied on the solid, it extends. On removing the load, it goes back to the original shape, original position, then it is elastic. If load is applied on the object, it deforms and it does not return to the original length. It has some extended length, some permanent deformation, then it is called the plastic behavior. So suppose load and extension graph. Extension at the x-axis force and the load force at the y-axis. This is the one of the graph. The end of the straight line is called the limit of proportionality. And the next point is called the elastic limit, meaning the end of the elasticity. And this is called the breaking point. Now the Hooke's law is applied only within the limit of probability, this line, but the elasticity is acceptable up to this elastic limit. This is the graph for the solid like metals. But if the solid is a glass, then this is the graph. It has no permanent deformation. This is force, this is extension. If the solid is a rubber, it's elastic. But extension and load both are not directly proportional. This is the loading line, and this is unloading line. Now the Hooke's law, extension is directly proportional to applied load within the limit of proportionality. So F is equal to KE or KX. And K is equal to F divided by E, units Newton per meter. What is K? The force required per unit length extension by the material. Force required per unit length extension by the material. Simply, for 1 meter extension, how much load is required? How many Newton forces required? That's K. And here, the gradient of the straight line is this K, which is material constant, spring constant, stiffness. And the area under the graph is the energy stored due to deformation, which is called strain energy or elastic potential energy. So the formula for the strain energy for the elastic potential energy will be 1/2 Fe. We are studying solids. If the solid is obeying Hooke's law, then 1/2 Ke into E. So it will be 1/2 Ke square. So either use 1/2 Fe or 1/2 Ke square. So same here. Gradient is K and the area is the energy. And here, look, we have two energies. One represented by this X, another represented by Y. Now, under this loading line, the area is X plus Y. I mean, this is actually the energy supplied for the extension. Work done on the rubber to stretch it. I mean, input energy. And this simply Y area under this unloading is the energy which is released while unloading. And this is loading. X plus Y is the energy supplied, work done for the loading, for stretching. And Y is the energy which is released during unloading. It means this energy is missing somewhere. This X is not released. It is absorbed by the material. So energy X is the energy which is absorbed by the material as heat energy. This is missing energy. That's why when the rubber is stretched number of times, its temperature increases because this X energy is absorbed by it. And this loss of energy during stretching and releasing is called hysteresis loss of energy. By calculating the area, we can determine that energy which is absorbed by the material. Okay, so Hooke's law, strain energy, elastic potential energy, and the next is strain. What is strain? Strain is the ratio between extension and the original length. Mean delta L over L naught. It has no unit. But when it is multiplied with 100, this is the percentage uncertainty in the extension. Percentage uncertainty in the extension. What is stress? Stress is a tensile force per unit cross-sectional area. Now, what is a tensile force? A force which is exerted at one end but felt by the object at the both ends. It is similar to the pressure, Newton per meter square, Pascal. If the solid is elastic, it obeys Hooke's law, then the ratio between stress and strain is called Young modulus. So the Young modulus is stress divided by strain. The stress is F divided by A, strain is extension divided by length, which can be written as F divided by A, L time over E. Or we can write F over E times L over A. It's obeying Hooke's law. The F over E is the material constant. So the Young modulus is equal to KL over A. K is the material constant, gradient of the force extension graph, L is the original length, and A is the cross-sectional area, which can be determined from the radius or diameter of the wire. Now, when the graph is plotted, stress at the y-axis and strain at the x-axis, then for the metals is similar to the force extension graph. The end of the straight line, limit of quality, next point is the elastic limit, this is the breaking point. But do remember, the gradient of the line is a Young modulus. And the area under the graph is not energy. It is the energy per unit volume, because 1 by 2 stress into strain, half base into height. So 1 by 2 stress is force divided by area, strain F over E, F over L. It can be written as 1 by 2 FE over AL. So this is energy, and area into height is a volume. So it is the strain energy per unit volume. Now, in this graph, if the object is unloaded beyond the elastic limit, it has permanent deformation. For example, unloaded from this point, then the unloading line will be parallel to the previous straight line. Both gradients are similar because the material constant is same. And this gap is showing the permanent deformation. This is the permanent deformation. Now, the experiment for the Young modulus. This is the wire. It is passing over a pulley. Suppose pulley is fixed here. To remove the kings, small load is attached here. So we will measure the length from this point to this point. Suppose here is a pointer, P. Measure this length with the help of the scale. Measure the diameter of the wire at 3 different positions, and then calculate the area. So diameter average, then area average, pi by 4 diameter square. And then measure the diameter of the pulley 3 times 2 times, so diameter of the pulley average. Now arrange some loads, hang loads one by one. After each load, the pointer will rotate towards right due to the extension. Suppose for the first load, the pointer goes to this position. Measure this angle with the help of the protector. And this arc length at the pulley will give you the extension. So the extension will be equal to theta divided by 360 into circumference of the pulley. Mean extension is equal to theta divided by 360 degree into pi diameter of the pulley. So use different loads and measure the extension by using this formula. And each time check whether the limit is crossed or not. Remove all loads if the pointer goes back to the original position. So the experiment is performed within the limit. Then different forces, different loads and extension graph plotted within the limit. For the force and extension, it will be a straight line passing through the region. Calculate the gradient, which is K, and then use the formula Young modulus KL over A, K gradient from the graph. L is the original length, A is the cross-sectional area of the wire. So we will determine the Young modulus. This is very, very important experiment. Okay, now the next important chapter, the wave. Definition of the wave, a process in which energy is transferred from one point to other without transferring any matter. There are two types of the waves. One is called the mechanical wave and other is called the electromagnetic wave. Mechanical wave is a wave which requires medium for the transfer of energy. And the electromagnetic wave, no medium required for the transfer of energy. Mechanical waves are produced by disturbing the medium, and electromagnetic waves are produced by perpendicular oscillation of electric and magnetic fields. And next, they are divided in two groups. One is a transverse wave, other is a longitudinal wave. If the direction of the vibration of the particle is perpendicular to the direction of the transfer of the energy in the wave, then it is called the transverse wave. And if the direction of the vibration of the particle is parallel to the direction of transfer of energy, then it is called longitudinal wave. For example, this is a wave. And it's carrying energy in this direction. Its particles are moving up and down. For example, the question is this particle, this particle, this particle. We have to show the direction of the particle's motion. So the simple method is, if the wave is going in this direction, move your finger in the opposite direction. Look, start here. At this point, your finger is going down. At this, your finger up, then up. So these are the direction of the motion of the particles. If the wave is going in this direction, you have to move finger in the opposite direction like this. Like this. So this is our direction. Now, the frequency is the number of the waves produced per unit time. And the wavelength is the distance between two consecutive in-phase points is called wavelength. Look at this wave. These 2 points, this one and this one. These 2 points are in phase because they are at the same displacement from the mean position. They are moving the same direction. So this gap, this one is the lambda. Now, distance is equal to speed multiplied by time. If we consider one wave, distance considered will be lambda, speed v, and the time taken by the one wave to complete itself is called the period. So the lambda divided by period is equal to speed, but 1 divided by period is frequency. That's why v is equal to f lambda. Now, the amplitude is actually the maximum displacement of the particle from the mean position in either direction. And the displacement is the distance of the particle from the mean position in a fixed direction is called displacement. And the intensity of the wave is the rate of transfer of energy per unit area of the wave is called intensity. And the intensity depends on 3 factors: amplitude square. That's why we can write I1 over I2, amplitude 1 square over amplitude 2 square, and intensity directly proportional to frequency square. And the third is intensity inversely proportional to distance square, distance from the source, distance from the origin of the wave. V is equal to f lambda. Now, if the graph is plotted, this is the wave, this can be distance, this is amplitude, this is displacement. Now, from this, we can calculate lambda. We can calculate amplitude. We cannot calculate speed. We cannot determine frequency. We cannot determine the time period from this wave. But if the same wave is plotted on the x-axis, having time, and here amplitude, then this will give you the period, frequency, amplitude, intensity. Yes, intensity can also be determined the first one because it depends on the amplitude, but this speed cannot determine wavelength and the speed. So when you have to determine the speed, which is equal to v is equal to f lambda. So frequency from this graph and the lambda from this graph. So for the speed calculation, both graphs are required. Next, what is the phase difference and what is the path difference? The path difference is the difference, linear distance. Difference in linear distances covered by the two waves before meeting at a point from their origin is called path difference. For example, one wave is traveling in this direction and the other wave traveling in this direction, and both are meeting here. So look at this, 1 lambda distance, second lambda, so it has covered 2 lambda distance. 1, 2, 3. Now the difference between 3 lambda and 2 lambda is called the path difference. So the path difference is represented in terms of the lambda. So 3 lambda minus 2 lambda is a lambda. And the phase difference is difference in angular distances covered by the two waves before meeting at a point from the region. Look here, this is 180-degree angle, mean pi radian. Angular distance pi. 1 pi, 2 pi, 3, 4. So this is 4 pi radian angular distance. And here 1 pi, 2, 3, 4, 5, and 6 pi. This is 6 pi radian distance. Now the phase difference is 6 pi minus 4 pi. So the phase difference is 2 pi radian. So the phase difference is represented in terms of the pi radian. And do remember, the ratio between the path difference divided by the phase difference is equal to lambda divided by 2 pi. And the next, suppose this is a wave. This is time, this is displacement. And the question is, sketch another wave which has 60-degree phase difference and double the intensity. 60-degree phase difference, double the intensity. Lags behind the first wave. Lags behind mean it is produced later. So at the time axis, the later wave is drawn ahead of the first wave. So suppose from this point to this, number of the small boxes are 30. We will count the number of the boxes on the graph. Suppose 30. Mean 30 boxes are representing one wave, mean 360 degrees. So the first 60 degrees, how many boxes? Unitary method 5. So we will start the new wave 5 boxes ahead. We will move the new wave. We will draw the new wave 5 boxes ahead. So its starting point will be 5 boxes ahead. 5 boxes ahead. End will be 5 boxes ahead. And the peak will be 5 boxes ahead. 5 boxes ahead. But double the intensity. Look, when amplitude becomes double, intensity becomes 4 times, because intensity directly proportional to amplitude square. But when intensity becomes double, amplitude increases under root 2 times. So suppose these are the 10 waves, 10 boxes vertically. So 10 multiplied by under root 2, it's approximately 14. We will shift this amplitude to the 14, to the 14. So this is the new wave. So which lags behind the 60-degree with a 60-degree phase difference and has double the intensity. Now, the waves are divided in 2 classes. One is the progressive, other is the stationary. Progressive wave is a wave which has net transfer of energy. It's a single wave, and it's carrying energy from one end to the other end. Mean 100% there is a shift of the energy, there is a transfer of the energy. But the stationary wave, it consists of the 2 waves. One wave is traveling in one direction and it carries energy, but the other waves travel in the opposite direction due to reflection from any hurdle and bring the energy back. So there is no net transfer of energy. And these points are permanently at rest. These are called the nodes. And these points are moving with the maximum speed, with the maximum amplitude. These are called antinodes. So node, 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 and node. But these points are antinode. If this node, as this antinode is moving up, then this will be moving down. This will be moving up. So within the loop, except nodes, all particles are in phase. But when they are compared with the neighboring loop, they will be out of phase. And the distance between two consecutive nodes, node to node, is lambda by 2. And the distance between two consecutive antinode is also lambda by 2, but distance between node and the next antinode is lambda by 4. And the stationary wave is used in the calculation of the wavelength, frequency, and the speed. Now, the intensity at the antinode is maximum, amplitude maximum. But at the node, it's minimum. For example, this is a microwave. It is reflected from the aluminum foil. The microwave is detected due to heating effect by the thermistor. When the thermistor is moved away from this, so here will be high intensity, high temperature, low resistance of the thermistor. Here will be low temperature due to low intensity, but high resistance. And again here at this, the temperature will be maximum due to high intensity microwave, and the resistance will be low. If we mark either two minimum resistance, consecutive minimum resistance, or to maximum resistance point, then measuring the distance between these 2 points, antinode to antinode, this is lambda by 2. So this distance is lambda by 2. So the lambda is determined 2D. All electromagnetic waves are traveling with the speed of light. So V is equal to F lambda. So V is the speed, 3 into 10 power 8. The frequency can be determined by using this formula. And similarly, we can use sound to measure the wavelength and the frequency of the sound wave with the help of the stationary wave. Okay, now a stationary wave in a pipe. Suppose this is a pipe which is closed at one end and open at the other end. For the first loud sound, the shape of the stationary wave inside the tube will be this. So the first overtone, first loud sound, one node and one antinode at the open end. So the whole length of this tube will be equal to lambda by 4. So the wavelength is equal to 4 times length. Now the second time, when the frequency increases, wavelength decreases. For the second time, when the loud sound is heard, 2 nodes are formed and 2 antinodes. So this is the shape of the wave. So this whole length is equal to node lambda by 2 and node to antinode lambda by 4. So lambda by 2 plus lambda by 4. So this is 3 lambda by 4, mean the lambda is equal to 4L by 3. So the sequence is tube open at one end, close at the other end. So first frequency is F0. So first wavelength for the overtone, loud sound is 4L. Then the wavelength becomes 4L by 3 and the frequency will be 3F0. Then it will be 4L by 5. So frequency will be 5F0. So it is increases by odd number, it decreases by the odd number. But if the tube is open at the both ends, then for the first loud sound, one node and 2 antinodes are formed. So this is node, antinode, antinode. So here the whole length is equal to lambda by 4, it becomes lambda by 2. So the wavelength is 2L. Now, second time, when the frequency increases, wavelength decreases. For the second louder sound, 2 nodes are formed and 3 antinodes. So antinode, antinode, and antinode. So this is lambda by 4, this is lambda by 2, this is lambda by 2. So whole length of the tube is equal to 2 times lambda by 2. Mean the lambda is equal to 2L by 2. So the sequence will be frequency F naught, the wavelength is 2L, then it becomes 2L by 2. So it becomes 2F naught, then it becomes 2L by 3, 3F naught, then it becomes 2L by 4, so 4F naught, and so on. Mean frequency increases by integers 1, 2, 3, 4, 5, and the wavelength decreases. Look, this is 2L by 1, 2, 3, 4, and so on. So this is the stationary wave. Now next move to superposition. Superposition is actually when two waves meet at a point. When two or more waves meet at a point, a resultant wave is produced. This is called superposition. And the principle of superposition is when two or more waves meet at a point, displacement of the resultant wave is the algebraic sum of the displacements of all individual waves. And then if the waves are coherent, mean their path difference constant, phase difference constant, mean their frequencies are equal, then the superposition of the wave is called interference. And the condition of the interference is, number one, both waves must be coherent. Both waves must be of the same type, both longitudinal or both transverse. But if both are transverse, then make sure both must be either polarized or unpolarized. Polarized mean any wave which is transferring energy only in single plane, single direction, and unpolarized, which is spreading the energy. So either both polarized or both unpolarized. Third, they must be in the same medium and meet at a point. So these are the conditions for interference. Now, if the path difference between the two waves at a meeting point is n lambda whole times lambda, then the constructive interference. So there are two conditions for the constructive interference. Number one is this, and the number two is both waves must be coherent. And the second, if the path difference between two waves is n½ lambda, then this is destructive interference. They will be having the phase difference of 180 degree, crest over trough. And the second condition is both waves must be coherent for the destructive interference. And the next is the diffraction spreading of the wave from the slit, from the aperture, from the edge is called diffraction, spreading of the wave from the aperture, from the slit, from the any edge is called diffraction. Now there are two types of the diffraction we have to learn. One is the double slit and the other is diffraction by the grating. So look, this is the light source, monochromatic light, single color light. And here is a lens. The gap between these two is equal to focal length of the lens. So all light coming from the bulb passing through the lens will be parallel to each other, and they are falling perpendicularly to the slit. So this is a requirement for the double slit diffraction. Now, light waves are spreading out. These two waves are coherent. Two different sources cannot be coherent. So this source is divided into sourcelets. This is S1 and this is S2. And this gap is called slit separation. And its value is approximately 0.3 millimeter to 3 or 4 millimeter. So here is a refraction, here is a diffraction, and here is the interference. So the number of the bright spots and the number of dark spots due to constructive interference, bright spot, due to destructive interference, dark spot. So the central bright spot is N0, then N1, then N2, and so on. Similarly, N1, N2, so on. This N1 mean the path difference 1 lambda, N2 mean path difference 2 lambda, so on. So here the path difference is 0. So this is the brightest spot and the intensity gradually decreases. Our fringes are equally spaced. Distance between two dark or the distance between two consecutive bright is same. It is represented by X pose. So X is equal to lambda D divided by A. Lambda is the wavelength of the incident light, A is the slit separation, and the D is the distance between screen and this double slit. So number one, the X directly proportional to lambda. When lambda increases, slit separation increases, intensity of the bright decreases. Number two, X directly proportional to D. When the distance between the screen and the slit increases, spacing increases, intensity decreases. And number three, X is inversely proportional to A. When the slit separation increases, separation between the fringes decreases and intensity increases. So this is the formula. X is equal to lambda D. If the polychromatic light is used, mean the white light, then the central fringe will be bright and the rest of the fringes will be colored, because each color has different wavelength. So different wavelength, different spacing. So longer the wavelength, longer the spacing. So that's why the red will appear here and the violet will here in this. But here, this is the red and this is the violet. Mean red is far from the center and the violet close to the center due to the smaller wavelength. Next is diffraction by the grating. Now, number of the engraved lines per unit length of the glass or the plastic sheet is called the grating, and that is the number per unit length, and this length is usually in millimeter. And the gap between two engraved line is called the grating spacing. D, that is L divided by N, or you can write 1 divided by G, and usually it is from 1 micrometer to 3 micrometer. So in diffraction grating, due to smaller grating spacing, the brightness of the bright fringes is greater than the double slit. Now, suppose this is the light. This light must be parallel and perpendicular to the grating to keep the path difference constant. And here's the screen. So this is the central line. All angles are measured from this line. So this is N1. So this is θ1. And so on. So here the formula is d sine theta is equal to n lambda. And n is the number of the fringe. For the constructive interference, bright fringe, it is called maxima. So here, d sine theta is the path difference equal to n lambda. Mean we are talking about the constructive interference, mean the number of the maxima. And lambda is the wavelength. D is equal to the grating spacing and the angle from the center. For example, this is the second one. So n is 2, angle theta 2, and this. So formula is this. So d sine theta is equal to n lambda. So the dark spot is called minima and the bright spot is called maxima. So when you have to calculate this n, you have to write the n in the whole number. If it's coming 3.7, so we will write it 3. If the question is what is the total number of the maxima appearing on the screen, so this central is 0, 3 this side, 3 this side, and at the center 1. So if n is coming 3, then the total number of the bright spot on the screen will be 3 plus 1, it will be 7. And then for the electromagnetic wave, you have to remember the wavelength range for the visible light, 350 nanometer to 650 nanometer. This is the wavelength of the visible light, VIBGYOR. So usually green is 500 nanometer. So less than this, ultraviolet, and more than this, infrared. Now, move to the next, electricity, current, electricity, and DC circuit. So first of all, what is electric current? Rate of flow of charge in the conductor is called electric current. I is equal to Q divided by T. Charge in coulomb, current in ampere, time in second, and the charge carried as an electron, its charge is fixed. It is represented by E. So the total charge will be NE over T. So I is equal to NE over T. Now, this N, the number of electrons. E is the charge, T is the time. So number of the electrons per unit volume of the conductor is called number density eta. So the number of electrons is number density multiplied by volume, and the volume is area into length of the wire. So when this N is replaced with number density AL multiplied by E divided by T, this L divided by T is the distance divided by time speed. So the other formula for the current will be number density A E into speed. Next is the potential difference. Work done per unit charge to move it from one point to the other point is called the potential difference. It is measured in volt, and EMF is the work done per unit charge to move it in the whole circuit, or energy supplied per unit charge to move it in the whole circuit is called EMF. And the potential difference is energy delivered per unit charge across the resistor is called potential difference of the voltage. So EMF, voltage, terminal potential. Look, the EMF is the energy supplied per unit charge by the battery. It is lost across the internal resistance, and some is transferred to the output circuit. That is called terminal potential. So the difference of the EMF minus the loss potential in the battery, that is called terminal potential. That is called potential difference or voltage. Now look, according to Ohm's law, voltage is directly proportional to electric current, provided the resistance, mean the temperature is constant. So V is equal to IR, and R is equal to V over I, mean the ratio between voltage and current in the conductor is called its resistance. Now, resistance does not depend on the voltage and current, because voltage and current both are directly proportional. Resistance depends on the temperature. It depends on the length, and it depends on the cross-sectional area. That's why at constant temperature, resistance is equal to rho L over A, where A is the cross-sectional area. Mean number one, resistance directly proportional to length. Number two, resistance inversely proportional to area. And number three, from this two, resistance is inversely proportional to diameter square. When diameter becomes double, resistance becomes 1/4. Area becomes double, resistance becomes half. Okay, then the graph, if the object, if the metal is ohmic conductor, then the graph between V and I is a straight line passing through the region. Ohmic conductor, mean the temperature constant, resistance constant, gradient is resistance. But if it is filament lamp, then with the passage of time, as the current flows, energy is dissipated as a form of heat its resistance increases. Resistance of the filament increases, so it's a graph. Gradient is increasing. So one for the ohmic conductor, other for the filament, and now the next semiconductor, thermistor. The graph is this, because when temperature increases, thermistor resistance decreases. And the next is energy. Electric energy is equal to charge multiplied by voltage. Power is equal to IV. Power is equal to I square R. Power is equal to V square divided by R. And the energy lost in the form of heat is I square RT. Now suppose the resistors are connected in parallel. So Kirchhoff's first law is applied, which is sum of the current entering the junction is equal to sum of the current leaving the junction, which is also called the law of conservation of the charges. So the current divides, so I is equal to I1 plus I2 plus I3. And I is equal to Q by T. So Q divided by T, Q divided by T1 plus Q2 divided by T2, Q3 divided by T3. But there is no delay between entering and leaving the current in the junction. So all T's are cancelled. So Q is equal to Q1 plus Q2 plus Q3. It means this is the law of conservation of charges. But if I is replaced from the Ohm's law, I1 plus I2 plus I3, I is equal to V by R. In parallel, the voltage remains same. So V divided by R1, V divided by R2, V divided by R3. When V's are taken common, cancelled. So the total resistance becomes 1 over R1, 1 over R2, and 1 over R3. Now look, in parallel, total resistance decreases. For example, this is a battery. First, this is the resistance R, and the current supplied is both I. When two identical resistors are connected parallel to each other, resistance decreases, it becomes R by 2 total, and the current becomes double. This double current, but each resistor will get the same current I and I, but current is added due to the parallel combination. Next, if the cell has internal resistance is shown inside the box, dotted box. This is EMF, internal resistance is. Now this is the resistance. Now, suppose the current is I. Now, due to the current, energy is lost here. What is energy? E is equal to I square RT. This is the energy lost here. Potential is lost here. The potential lost is equal to IR. And the voltage provided to this resistor is not EMF equal to EMF. This voltage is equal to EMF minus IR. Now, when same cell, same internal resistance is connected with two parallel resistor, its resistance same R, EMF E, but now the resistance becomes half. So the current becomes double than the previous. So due to double current passing through this R, more energy is lost, more potential is lost. So lost potential becomes 2IR. So the less potential, less voltage supplied to it. So the voltage supplied will be here, EMF minus 2IR. So do remember, when the current increases, loss in the internal resistance increases, Thus, the terminal potential means the voltage potential supplied to the external circuit decreases. Now, suppose resistors are connected in series. So current remains same, voltage is divided. So V1, V2, V3. And Kirchhoff's second law is total EMF supplied to the circuit is the sum of all potentials across the resistors in the circuit. Mean total EMF will be V1, V2, and V3. Now, the EMF is energy per unit charge. This is EMF. So total energy divided by charge. Here, the energy 1 divided by charge 1, energy 2 divided by charge 2, energy 3 divided by charge 3. But the charges are same, the current same. So all charges are taken common cancelled. So this is the law of conservation of energy. Law of conservation of energy. Next. Now, if this EMF, again written V1, V2, V3, Kirchhoff's second law, according to Ohm's law, EMF is equal to IR total, then IR1, IR2, and IR3. So when I is taken common cancelled, so the total resistance in series, it will be R1 plus R2 plus R3. So in series, total resistance increases. So due to the resistance increase, current in the circuit decreases. When the current in the circuit decreases, loss in the internal resistance decreases, but the potential to the circuit, mean the terminal potential, increases. Next is the potential divider. Look, when two resistors are connected in series, they divide potential, distribute potential, and the potential difference formula is Vx is equal to Rx over Rx plus Ry into EMF, which shows that the voltage is directly proportional to resistance. When two resistors are connected in series, they are having the same current, V is equal to IR, so voltage directly proportional. Mean, in potential divider, the ratio between the two voltages exactly equal to the ratio between two resistors, and the resistor depends on the length are directly proportional to L. If wires are used instead of the other resistors, then L1 over L2, but the resistance inversely proportional to area. So inversely proportional, so this is L1 over L2, so it will be A2 over A1, and similarly, it will be diameter 2 square over diameter 1 square. So these are the relations. Now, in potentiometer, this is the resistance wire, A and B. So do remember, unknown cell must be connected parallel to the previous. So this is positive, this positive. And here, any galvanometer, ammeter, we will find the balance point, mean the point at which the ammeter reads 0. So suppose this is the balance point. And the total length of the wire is L, and the balance point length is suppose X. Then the formula will be voltage divided by EMF of the cell. This voltage of this is equal to X divided by L, mean the voltage of this unknown cell is balance point length divided by total length of the wire multiplied by EMF of the circuit. And then the next is the maximum power theorem. Suppose the power output from the circuit, and this is the resistance, then the graph will be like this. So the maximum power P0 is achieved when external resistance exactly equal to the internal resistance of the cell, internal resistance of the circuit. Now look here, the resistance is smaller than this. So due to small resistance, the current is large. And here the resistance is greater, so the current is smaller. And do remember, the gradient of P over R, mean gradient, is current squared. So that's why this gradient is large, this gradient is small due to the current. Now, any value lower than the peak value, for this value, will come twice. Number one, number two. This small resistance, large current. This large resistance, small current will give you the same value, because when the resistance is small, current is large, and the power is the product of current square and resistance. When the resistance is large, current small, you can get the same power. So this is the electricity. Okay, next, nuclear physics, radioactivity. First of all, the size of the atom is 10 power minus 9 meter or 10 power minus 10 meter. And the size, mean the diameter of the nucleus, either 10 power minus 14 meter or 10 power minus 15 meter. And the mass of the atom exactly equal to the mass of the nucleus, and the mass of the atom or the nucleus is A times U. A is the atomic mass and U is AMU, atomic mass unit. So it's 1.66 into 10 power minus 19. And the density of the atom, mass per unit volume, but the volume of the atom is greater than the volume of the nucleus, so density will be different. So for the volume of the atom, for the volume of the nucleus, instead of 4 by 3 pi r cube, you can use just diameter cube for the volume. And do remember, the density of the nucleus is too large as compared to the density of the atom. Mass same, volume large of the atom, so density small. So the density of the nucleus is greater than the density of the atom due to its large volume, but mass is same. Now, according to alpha scattering experiment, most part of the atom is empty because the majority of the alpha particle goes either straight or show small deflection. Only few particles are deflected with the angle greater than 90 degrees. It means the central part is dense and positively charged, which is later called the nucleus of the atom. Okay, now the particles inside the nucleus, they are called hadrons. They are made up of quarks. So you have to remember up and down quarks. So proton is the famous hadron. It has 2 up quark and 1 down quark. Up quark has charge plus 2 by 3 elementary, and the down quark has charge minus 1 by 3 elementary. And the neutron has 1 up and 2 down quark. That's why it's neutral. And if any particle inside the nucleus contain anti-quark along with the quark, that is not called the hadron, that is called the baryon. And all these hadrons are under the influence of the strong force, and the strong force is effective only inside the nucleus. That's why its range is just the size of the nucleus, 10 power minus 14 meter, 10 power minus 15 meter. And outside the electron, inside the nucleus, all particles are leptons. Leptons are considered the fundamental particle because they have no further division, but hadrons are not fundamental particle because they are composed from the quarks. You have to remember up, down, top, bottom, strange, like this, and anti-quark, anti-up, anti-down, all quarks. And then leptons, famous leptons are electron. Anti-electron is called the positron, neutrino, anti-neutrino, like this, okay? So they are revolving outside. They are under the influence of the weak force outside the nucleus. Look, when a neutron is converted into proton, beta particle is emitted along with the anti-neutrino. When proton is converted into neutron, this positron, mean anti-electron, is emitted and neutrino itself emitted. Next, if the proton number, means Z, is greater than 83, or the mass number greater than 200, the atom, the nucleus, is called natural radioactive, unstable. For the stability, it emits radiation. And these radiations are alpha, beta, and gamma. And this process is totally random. No one can predict which nucleus will emit radiation next time, how many radiations will be emitted, and what will be the emission of radiation. Mean it's random in terms of number, in terms of direction. And this process is also spontaneous. Mean no force is required to emit alpha, beta, gamma. So it is not affected, mean the rate of emission is not affected by the surrounding physical condition, by the change of temperature, by change of the pressure, no effect on it. And the time taken by any radioactive sample to decay, it's half of the sample after emitting the radiation, that is called the half-life. Now, alpha is positive charge particle. It is similar to the helium nucleus. It has +2 elementary charge. It is emitted from the nucleus with a speed 1/10 multiplied by the speed of light. It penetrates up to 5 or 6 centimeters in air. Its ionization power is large, approximately 10⁵ ions per millimeter in the air. Ionization power is large. It is deflected in the electric and magnetic field. And similarly, the beta is also a particle. It's similar to the fast-moving electron. Its mass is very small compared to the mass of the alpha particle, because alpha particle, 2 proton, 2 neutron. So the mass of the alpha is 4U, where U is 1.66 and 10⁻⁻⁻27. And the mass of the electron is 9.11 into 10⁻⁻31. It's too light as compared to the alpha. It has -1 elementary charge. It is emitted with a speed which is 90% to 99%. Its speed is not fixed, because along with the beta emission, other particles also emitted. They share the energy. So when the energy is shared, then definitely no fixed energy of the electrons. No fixed energy mean no fixed speed. Its ionization power is smaller than alpha, approximately 10⁻³ ions per millimeter in the air. Its penetration power is approximately 100 centimeter in air. Alpha is blocked by the paper. Beta is blocked by the aluminum sheet, right? It is also deflected in electric and magnetic field, but its reflection is greater than the alpha, because alpha is heavy and it is deflected in the opposite direction as compared to the alpha deflection. Next is the gamma. It's not a particle. It's a radiation, electromagnetic radiation. No mass, no charge. It is emitted exactly with the speed of light. It's not affected by the electric and magnetic field. It has least ionization, approximately 1 ion per millimeter in the air. And its penetration is very high, few kilometers in air. It is not deflected in electric and magnetic field. And it leaves no effect on the proton number, mass number, neutron number. But when alpha is emitted, totally new element is formed. Proton number decreases by 2, mass number by 4, because alpha is 2, 4 along with energy. Similarly, when beta is emitted, it is new element, suppose P. Proton number increases by 1 because the neutron is converted into proton. mass number remains same, beta particle is emitted, and some energy, and some particle. And if this element is emitting the gamma, it remains same. For example, uranium is emitting alpha, then it is converted into thorium. If uranium is emitting beta, it is converted into neptunium. If the uranium is emitting gamma, which is just a radiation, no effect. So due to alpha emission, proton number decreases by 2, neutron number decreases by 2, mass number decreases by 4. And due to beta, proton number increases by 1, neutron number decreases by 1, and the mass number remains same. And the gamma, no effect on proton, no effect on the neutron. Now the graph, suppose here the proton number and here the mass number. This is suppose the X element, it is emitting alpha, 2 proton decreases, and 4 mass number decreases. If the graph is between proton number and the neutron number, this is element emitting alpha, 2 proton number decreases and 2 neutron number decreases. This is for the alpha. Now for the beta, for example, this is proton number, this is the mass number, this is the X element, it's emitting beta. So proton number increases, mass number remains same. This is the proton number, this is the neutron number, this is X. Beta emission, proton number increases, neutron number decreases by 1. 1 proton increases, 1 neutron decreases, so new element. And gamma leaves no effect, so no graph. Now the number of the radioactive elements, number of the radioactive nuclei decaying per unit time is called decay constant. So dN over dt is called decay. dN over dt, not decay constant, dN over dt, this is called decay rate, and decay rate is also called the activity, and dN is called decay. And this decay rate depends on the number. For example, we have initially 1000 element. After half-life, they are 500. After second half-life, they are 250. Look, here the decay rate is 500 divided by half-life. And here the decay rate, 250 divided by half-life. Half-life is fixed. So look, this answer is greater than this answer. It means larger the number, larger the activity. Smaller the number, smaller the activity. So when the graph is plotted, time and n, so this is n naught. So the radioactive nuclei are decreasing and their daughter nuclei are forming. So the radioactive nuclei are decreasing in the number, but the new element are increasing in the number because uranium converted into neptunium, uranium converted into thorium. And the time taken by any radioactive sample to decay its half is called the half-life. Now this radioactive decay is a random process, spontaneous process. But if there is no visible source of radiation, no radioactive source visible, then the number of the radiations detected by the GM tube are called background radiations. So the radiation detected by any detector without any visible source, they are called background radiation, BGR. That's why when we will plot the graph, count rate against time, it will never touch to the zero line. It becomes constant. So this is the background radiation, which are usually 20 to 30 radiations per minute. And there are many sources. You have to remember the sources for the background radiations. Any radioactive rock underground, you have to prepare the percentage, any leakage, food, hospital waste, radioactive waste, like this. Okay, now quick look at this formula sheet. You have to remember this, you have to learn significant figure, uncertainty formulas like this. So each and everything with detail is given here. So this is the summary of this paper 2. And then next are the kinematics. This is very, very important before the exam, a day before the final exam. Then dynamics, then density, turning effect, force formulas, then work, energy, and power, each and everything, efficiency. You have to learn these. So this is the electric field strength. So you have to remember in electric field strength, first the definition of the electric field, area of the region around the stationary charge in which a particle experiences force. Electric field is radial. Line represents the direction of the test charge, and the arrow represents the direction of the motion of the test charge, and line represents the path followed by the test charge. Electric field strength, E is equal to V by D. And electric field strength is also F divided by Q. Then the electric field drawing, radial field, isolated charges, then electric field between the two plates, uniform field, and calculation of the electric field. E is equal to V divided by D. V is the potential difference between the two plates and D the separation. Then the force F is equal to EQ. This force is unbalanced and constant in the uniform electric field. Next, acceleration of the electron, F divided by M. Then final speed, V is equal to U plus AT, or simply V square is equal to U square plus 2AS. And then two plates, one connected with the positive, other connected with the negative, uniform. Here the charged particle can be made stationary if the plates are horizontal, parallel, and the charge is opposite to the top plate. Parallel, uniform field, horizontal, vertical force to cancel the effect of the weight. So in this situation, weight is acting down and electric force up. This is positive, this is negative force minus weight, the resultant 0. So F is equal to W, F is equal to EQ, W is equal to mg. So we can calculate charge to mass ratio, which is G over E. G is gravitational field strength, E is electric field strength, electrostatic force experienced per unit test charge. And the test charge is considered positive. An electric potential, work done per unit test charge, per unit positive test charge to move it from infinity to a point in the electric field. And charge Q also can be determined. Q is equal to mg divided by E. if this is a combination, this is positive plate, this is a negative plate. If the charged particle enters here, suppose it's a positively charged particle. This is the electric force. It bends down. The horizontal velocity will remain same. So the time taken to escape the field will be the length of the plate divided by horizontal speed. And this vertical distance covered, when it leaves the electric field, this vertical distance will be S is equal to UT 1 by 2 AT square. This is vertical. Vertical initial velocity is 0. Acceleration calculated, time calculate this. If this vertical distance is smaller than this gap X, then the charged particle will escape the field. If it's greater than this gap, it will hit the plate. Next is the electric current. Potential difference, Ohm's law, energy, power, Kirchhoff laws, and then density, pressure, kinetic energy, potential energy, then deformation, formula, then Young modulus, strain energy, and then radioactivity, and the next, the important wave, period, frequency, wavelength, wavefront. Yes, wavefront, an imaginary line joining all points at the front of the wave, which are in phase, is called wavefront. And the wavefront represents the crest of the wave. Distance between two consecutive wavefront is equal to wavelength. And then diffraction, polarization, stunning, stationary wave, speed of light. And then next, this is important. You have to remember these wavelengths, okay? Okay. So, end of this shortcut. So look at this. So you have to prepare question 1 about this topic, question number 2, question number 3, question number 4, question number 5, 6, and 7. Look at this. So this is the shortcut for the last moment, okay? So this is the revision, and this is the summary of the whole syllabus. Good luck.